let's talk about conservation of momentum really quickly. You're already familiar with the concept of conservation of momentum, and if you can find out about the movement of the centre of mass before, during and after collisions, you can use that to solve conservation of momentum problems, whereas before you've only had one way of solving them. And this way is particularly useful for when you have situations where things are moving at angles to one another. So instead of having to calculate vectors directly, you can use the centre of mass between them and then separate out the movement of the components. It makes things a lot easier when things move off at angles. So let's take our example here. We've got two ice skaters, one with pigtails, one with spiky hair, and one with pigtails is moving towards our stationary one with spiky hair. And this one obviously has momentum, so they're moving, they have mass, they have momentum. This one here has no momentum at first, they're not moving at all. But there is still a total momentum in the system between them. So wherever their centre of mass is, and of course that depends on which one's big. So let's say our spiky head one is the larger of the two, the centre of mass is going to be closer to our spiky head one. And remembering the velocity of the centre of mass depends on the total momentum, which is contributed by pigtail person, divided by the total mass contributed by both of these. So the velocity of the centre of mass will not be the same as the velocity of our one moving person. Let's move on to the point where they've collided. And at this point here, the velocity of the centre of mass is still moving. They haven't collided and stuck together. We're just seeing them in an instant in time before they spring apart or do whatever it is that they're going to do. And in our case, we're saying, well, at this point here, the centre of mass is still between them, wherever it happens to be. And then it's still moving, it still has that velocity. So if we were to say, well, over here, let's say this is where our centre of mass is, and let's say this is its velocity of the centre of mass. We could say, well, over here, here's our centre of mass, and here's the velocity of our centre of mass. It's still the same. Same direction, same size, same velocity. Total momentum of the system, the same. If we come down to here, to a point where they have separated from one another, we can see that our pigtail person has moved away at quite a sharp angle, and they've moved quite a long distance. They have moved further away from the plane that they were previously moving on. So we can see that they are now moving off, say, in these directions, but the centre of mass is going to be the same. So if we look, it's still going to be between them, okay? And I know my diagram is not very exact, but it's still going to be between them, the same proportion as it was here, depending on their masses. It's still going to be between them, and it's still going to have the same velocity. Now my diagrams aren't very good, but if you have a think about how this works, you'll be able to see for yourself that even when they're moving off at these angles, those ratios, the ratios of distance will stay the same, and the movement of the centre of mass will stay the same.